Hi everyone, I'm Dario, thank you for having me. In this presentation I'm going to talk about the full pose manipulation control of a cable suspended load with multiple UAVs considering uncertainties. Full pose control is possible when the robotic system can attain a 6-dimensional range of the load. Srinath demonstrated that the minimum setup that possesses such ability is a system with 3 vehicles connected through cables to 3 non-collinear points of the load. Drawbacks of such configuration are, first of all, we cannot exclude possible load internal motion. It's not possible to constrain some load motion in some directions. The consequence, and here we are in the second point, the overall system results sluggish and imprecise. Ideally, we would like to have a design that can compensate external wrenches almost instantaneously without the need of moving the robots. We are then interested in statically rigid or forced closure designs. So for a full pose control, which means for a 6 degrees of freedom control, at least 6 attaching points are needed. Masone proposed a solution with 6 robots and 6 cables, but besides to be a highly redundant system, it is more dangerous, more expensive, and difficult to be maintained. Motivated by this analysis, let me introduce to you our solution, the fly crane. Firstly proposed by Manubens, it is made up of 3 robots, 6 cables and 1 platform. Doing so, we choose 3 robots, that is the minimum setup in terms of the number of robots, and we can fully control the load as a result of opting for 6 cables. Please notice that the choice of using 3 robots allows 9 degrees of freedom, so that 3 are redundant, and that for this reason the fly crane is a redundant manipulator. We ended up with a kinematic model for the fly crane. Why? Manageability in terms of the mathematical formulation is a pivotal aspect, but also consider that for manipulators all the dynamic aspects are negligible when they produce quasi-static motions. However, we do not entirely forget dynamic aspects. Model errors and model uncertainty will be strongly considered. Going to the mathematical details, the position of each robot PR rigidly depends on the load position PL, the load orientation RL, and the so-called dihedral angles alpha J. They are the angles created by the platform and the cables. From now on, let me call load position, load orientation, and dihedral angles as platform configuration Q. The kinematic model then relates the robot position PR and the platform configuration Q through F function. Let me differentiate this function. Now, .PR, the robot speed, is equal to JQ Q dot. JQ is our Jacobian. In the end, we can handle robot speeds as our inputs, causing platform motions as our outputs. This is obtained by applying a kinematic inversion. As a consequence, we build up an inverse kinematic controller to control the multi-robot system. In our schematic, this represents the outer loop. The generated velocities are then commanded to the robot that will track them through a geometric tracking control in ST3, our inner loop controller. The inner loop is a proportional derivative controller on the error in velocity, where VR are the actual robot's velocities and VR star are the references. Instead, the outer loop is a proportional controller on the platform configuration error Q desired minus Q plus a feed-forward term. With this choice, we try to keep a very slight error, avoiding sudden changes. Since we are applying a proportional controller on the error, let's have a look at the error dynamics. Written in this way, it is asymptotically stable in nominal condition. But what happens if we consider uncertainties? Common uncertainties in real systems are parametric and actuation uncertainties. Parametric uncertainties are all those issues related to the imprecision in the design and manufacturing of the platform. The cable lengths and the attaching point were our case studies. They closely affect the Jacobian that from now on will have the form J at is equal to JQ plus delta JQ. Actuation uncertainties are instead all the dynamical disturbances D that can arise in the robot's models. Dealing with all these uncertainties allow us to perform robust control. Summarizing and going back to the controller schematic, we can replace the equation with the new ones in which we have the new Jacobian form JQ hat and the actuation disturbances D. And going back again to the error dynamics and considering all the uncertainties in its equation, this time there is no guarantee that the dynamical system is asymptotically stable. And you may observe that our two new terms came into being. At this stage, it is meaningful to look at the ratio between the error and the disturbances. It determines the error amounts as a consequence of a disturbance. For example, on the top left corner, the error will be significant as a consequence of a small disturbance. On the bottom right corner, the error will be tiny as a consequence of a significant disturbance. As you can imagine, we would like to hold up our function error over disturbances on the bottom side. For this reason, I'll show you how to design the configuration control gain such that to guarantee the stability of the closed-loop system with the desired H-infinite performance under some sufficient conditions on the uncertainty and disturbance magnitudes. We talked about sufficient conditions. On what? On the Jacobian bounding the model errors and along the possible configurations that the system can reach. Regarding the performance index, instead we took advantage of the H-infinite control technique. It substantially guarantees that the system will not deviate from expected trajectories when disturbances enter it. Imagine having a particular output signal Y and an input signal X. H-infinite control allows to bound the ratio between output and input through the H-infinite performance value. The idea applied to our problem is to maintain the ratio bounded behind our H-infinite index. To this aim, we define a linear matrix inequality problem to minimize it. Going to the results, we executed our testing for different conditions. The first one is in optimal condition, considering then the model error, simulating an external disturbance like the wind, and finally despite out of scope even in tracking a fast trajectory. In optimal condition, the model parameters are the one measured with no additional errors. Notice that, however, the measurement errors and noise are still present. In this other case, we added an error on the length of the cable equal to 10% of their nominal values. For example, for a cable length of 1 meter, we had 10 centimeters more of uncertainties. As you can see from the graphs, while all the sufficient conditions are satisfied, the error results bounded from the disturbances. This confirms that the chosen bounds are precise enough. In this other scenario, we added an artificial force equal to 1.7 Newton to the aerial vehicle's low-level controller in each direction. Even in this case, the error keeps staying bounded by the disturbances while the sufficient condition persists in being satisfied. It was also enjoyable performing some experiments trying to stimulate our system with more challenging trajectories. In conclusion, we implemented an inverse kinematic controller for the fly-crane system, together with a tuning method which ensures stability and maximizes the robustness against uncertainties and external errors. Finally, we verified the system and the control frame of validity in real experiments, realizing the aimed full pose control of the platform. Despite this, a good number of insights can be addressed. One of them is to extend the controller to a second-order kinematic approach. The second one is extending the analysis of the center of mass estimation of the platform when one might place either fixed or either floating masses. One other topic might be exploring the fly crane redundancy, in equally distributing the load over the quad rotors, in saving energy while executing the task, or in maximizing the distance from possible obstacles. Last but not least, moving the system in an outdoor environment, performing outdoor experiments. By saying this, I finished my presentation, so thank you for watching.